Hello everyone, myself Dr. Deobroto Bhadro. I taught physics at Bhairav Ganguly College, Belghoria. Our topic of discussion today is a very well-known uh, in physics, that is particle nature of light and wave nature of matter. To begin with, this is the course content that I will touch upon in the successive uh, periods of this lecture. And to begin with, I will discuss the photoelectric effect, and then I will discuss the Compton scattering. So from the last two levels, we all know that the photoelectric effect was initially observed by Henry Hertz in 1887. That is, the polished metal plates that are irradiated, it might emit electrons, which are called photoelectrons, and the emitted electrons thus produce a photoelectric current. And he also opined in this successive experiment that there is a threshold frequency, that is nu naught, and for frequencies which is higher than nu naught is there a photoelectric current, and the frequency nu naught which depends on the metal and the configuration of the atoms at the surface. So it is also affected by inhomogeneities. The other feature is that the magnitude of the photoelectric current is proportional to the intensity of the light source, and also the energy of the photoelectrons is independent of the intensity of the light source. To be precise upon, we also discuss by a common topic, that is a natural explanation for the features of this effect before Einstein. And when Einstein explained the above feature of the postulating that the energy in light is carried by discrete quanta, and later which he called photons, with energy h nu, where h is the Planck's constant and the constant used by Planck to produce fit for the black body energy as a function of frequency. So that's why if we plot this type of diagram, that is, if my y-axis is denoted by E and my electrons are based upon this, this is my electrons, okay, and you have to have energy of this height, that is the work function. For a particular model, we have discussed that electrons in a metal are always in a bound state, as we know, and if the photon energy is greater than the work function, that is W, then an electron may be ejected. So a given material has a characteristic energy W, that is the work function, which is the minimum energy required to eject an electron. This is not easily calculated because it is in the result of an interaction of many electrons with a background of atoms. So it is easily measured. However, when the surface of the material is irradiated and the electrons in the material absorb the energy of the incoming photons, if the energy of imparted on an electron by the absorption of a single photon is greater than the work function W, then the electron is ejected with kinetic energy. That is, my electron energy is, as we know, half mv square, and this is my h nu minus the work function, and this would be equal to, that is, E nu or E nu minus W. This equation is written by Einstein. This equation is written by Einstein, which explains the experimental features of the noted. Once we assume that the quanta act on individual electrons to eject them, so the threshold frequency is defined as my h nu naught, is equals to the work function W. As it reads to the photoelectron with the zero energy, for nu greater than nu naught, the electrons will be ejected, and the increasing the intensity of the light source increases the rate that photons arrive, which will increase the magnitude of the current, and but will not change the energy of the photoelectrons, because it does not change the energy of each incoming quanta. So as we go further, that you can see from the slides that E is a multiple of h nu, that is hc by lambda, where h is the Planck's constant, and following properties of photons can also be followed, where the photon travels at the speed of light. As we know, it has the zero rest mass, and it cannot exist at rest, and the kinetic mass of the photon is h by c lambda, and also the momentum of the photon is p by lambda. Photons travel in a straight line, and the energy of the photon depends upon the frequency of the photon. Later on, the Einstein's prediction was also followed by the Millikan, who confirmed experimentally where carefully the photoelectron energies, and confirmed their linear dependence on the energy, and Millikan's careful work allowed him to determine the Planck's constant h cut later on. So in this context, let us discuss about the a simple problem. Not a problem, but general understanding. Suppose you have the UV light. UV, as we know, the wavelength of UV light lambda is equals to 290 nanometer, is incident on a metal, and with the work function W is equals to 4.05 of electron volt, and so that with the given condition you are given to calculate the energy of the photoelectron and what was its speed. So let us calculate this like a very simple fashion. As we all know that you have to remember this value. This is very important in physics, I think. That is the h cut c, where h is equals to, as we know, h by 2 pi, and this value is typical at the order of 197.33 mega electron volt femtometer, right? And as we know that MeV is the bigger unit, that is 10 to the power 6 electron volt, and femtometer is 10 to the power minus 15 meter, right? So let us use this formula to compute the photon energy. So in this case, our E nu, right, E nu is equals to h nu, that is 2 pi h cut times c by lambda. Then as we follow the formula, as we put the values of 2 pi times hc, that is 197.33 mega electron volt femtometer, divided by 290 into 10 to the power minus 9 meter, that comes out to be precisely 4.28 electron volt, right? And thus our electron energy, that is calculated from the Einstein formula, that is this formula, E is E gamma, or E nu minus W is nothing but E nu minus W, that is 0.23 electron volt. And with this we have to compute the energy. So far is 0.23 electron volt is nothing but the kinetic energy of the electrons, half me v square, that is half me c square times v by c whole square. And recalling that our me times c square is at the order of 511,000 electron volt, and one finds that 0.46 divided by 511,000 000, that is the order of V by C whole square, right? So it turns out that V by C at the order of 0.00094, and with our conventional C, that is 300,000 kilometer per second, right? We can get V as 284.4 kilometer per second. So let's estimate the velocity of the photoelectrons, and we can predict also the speed of those electrons. So from this important calculation, another one important feature we can calculate from here is one can calculate the that is the dimension of Planck's constant h, and the answer is that if as we all know, E is equals to h nu, and if you have to calculate the dimension of h, that is the dimension of E over dimension over nu, that is very simple calculated, m l square over t square, and this is 1 upon t. So it turns out that L times m L upon t. So this is the typical dimension of Planck's constant, where m, L and t are the units of mass, length and time respectively, and we have written the rightmost expression as a product of units of length and momentum, and therefore our h is nothing but the dimension of r cross p, that is the angular momentum, right? As we see that h has the units of angular momentum, and indeed for a spin 1/2 particle, the magnitude of the spin angular momentum is h cut by 2, right? From this calculation we can easily calculate or estimate the dimension or the physical interpretation of the Planck's constant. Next we move on that this typical particular behavior of photoelectric effect, where you can see that these UV light are being irradiated to the metals, and from this metal, if the photoelectrons are being emitted, so this is the particular phenomena where the electrons emitted in this effect is called the photoelectrons, and the content and the current corresponding to the electrons are called photoelectric current, and this is also being incorporated in our CBCS core 9 practical, I would say, core 9 lab, where photoelectric current versus intensity and other stuffs are being incorporated, where you can experimentally verify the particular phenomena of photoelectric effect, right? So this is a particular example where other than metals, you can see these metals other than alkali metals, and this is the behavior of the alkali metals, where visible light are being irradiated and there is no photoelectrons are being emitted, and if visible light are being irradiated to the alkali metals, as usual the photoelectrons are being emitted, right? So this is the particular behavior and the schematic diagram of the experimental setup to study the photoelectric current. And as you see this particular slide, I have detailed studied the UV light is being irradiated to the metallic cathode, and the metallic anode is being denoted by A. Then W is the quartz window, right? This is the window where this UV light is being irradiated, and the photoelectrons can go through the cathode to anode, right? And as we know that the light of suitable frequency that falls on the metallic cathode, the photoelectrons are being emitted, and these photoelectrons are attracted towards the positive anode, and hence photoelectric current is being constituted. So let's study the intensity versus current behavior and the potential of A versus I, where you easily seen from the slides that for a fixed frequency, the photoelectric current increases linearly with the increase in the intensity of the light. That is the linear behavior as we expect from the Einstein's photoelectric equation. And another important feature is the effect of the potential on the photoelectric current, as you see from this behavior that for a fixed frequency, you just look at the diagram particularly when for a fixed frequency and intensity of the incident light, the photoelectric current increases with increase in the positive potential applied to the anode, and when all the photoelectrons can reach to the plate A, current becomes maximum and it is known as the saturation current, as you see from the particular behaviors like this. And when the potential is decreased, the current decreases but does not comes to zero at zero potential, and this shows that even in the absence of the accelerating potential, a few photoelectrons manage to reach the plate on their own due to their kinetic energy. So the take-home message from these two plots are when a negative potential is applied to the plate A with respect to C, the photoelectric current becomes zero at a particular value of negative potential that would called the stopping potential, right? The stopping potential, and the other name of this is the cutoff potential, and the intensity of incident light does not affect the stopping potential, right? As we know from the plus 2 levels. So this is another important feature. You can see from these plots that the effect of the frequency of incident light on the stopping potentials, where a fixed intensity of incident light and the photoelectric current increases and is saturated with increase in the positive potential applied to the anode, and when the potential is decreased and taken below zero, the photoelectric current decreases to zero but at the different stopping potentials for the different frequencies. So as the higher the frequency, the higher the stopping potential, that is Vs is proportional to V, right? Vs is proportional to, this is particular Vs1, this is particular Vs2. These are the typical behaviors of the IV characteristics of the photoelectric current, and my x-axis is the potential of anode. I can measure it in voltage. So from this plot we can also suggest that our Vs is proportional to V, right? So threshold frequency, this is a particular dependence of the graph between the stopping potential and the frequency, which does not pass through the origin, and it shows that there is a minimum value of the frequency called the threshold frequency, what is known as nu naught, and it shows that there is a maximum value of frequency called the threshold frequency, below which photoelectric emission is not possible, however high the intensity of the incident light may be. So it depends on the nature of the metal emitting photoelectrons. So this is all about photoelectric effect, and this is the particular photoelectric equation as you see from these slides, right? And don't worry, I will upload it in the my YouTube video, and this would be the verification of the photoelectric emission based on the Einstein's photoelectric effect. And these are the few applications which we can try for the numerous applications of photoelectric effect, right from scanners in television transmission to the astronomy to the automatic switching of street lights. These particular behaviors are always in use of photoelectric effect. So up to this, I will also touch, as I promised, that uh, using the speed of light, we can construct the momentum p, that is momentum p is mc, and then the length L is obtained from the ratio h by p. This is actually the Compton wavelength, right? That is a LC, right, of the particle, and this lambda c is nothing but h by mc. Then has the units of length, and this is called the Compton wavelength of the particle of mass m. This is very important to note that the length is independent of the velocity of the particle, and the de Broglie wavelength of the particle uses the true momentum of the particle, not mc, right? My de Broglie would be the h upon mv, which is the true momentum, but in this case this is mc, not the true momentum of the particle. Thus the Compton and de Broglie wavelengths should not be confused. I repeat, the de Broglie and Compton wavelengths should not be confused, right? So from this, it is possible to get some physical intuition of the Compton wavelength lambda c of the particle. We claim that lambda c is the wavelength of the photon whose energy is equal to the rest energy of the particle. Indeed, we see that mc square is equals to h nu, that is hc by lambda. From this, lambda can be estimated as h upon mc, right? And once we use the light where lambda is less than lambda c, right, where lambda is less than lambda c, the photons carry more energy than the rest energy of the particle, and it is possible then the energy of the photons go into creating more particles of mass m, making it difficult, if not possible, to localize the particle, right? The Compton wavelength is the length scale at which we need the relativistic quantum field theory to take into account the possible processes of particle creation and annihilation. So let us calculate the Compton wavelength of the electron, that is lambda c of electron is h upon mec, that mass of the electron and the velocity of light in vacuum. It can also be written as 2 pi h cut c upon mec square, the rest mass energy of the electron, and as we know the values, that is 197.33 mega electron volt femtometer versus 0.511 mega electron volt, and this turns out to be 2.426 picometer. You see the range of this. The Compton wavelength is 2.42 picometer. The length is about, you can say, it's 20 times smaller than the Bohr radius, that is 53 picometer, and the another length scale is that it is about 2000 times the size of the proton, right? 2000 times the size of the proton, that is 1 femtometer. So the Compton wavelength of the electron appears in the formula for the change of photon wavelength in the process called Compton scattering. So what is Compton scattering? Originally, Einstein did not make clear that the light quantum meant I would say a particle of light, right? In 1916, he posited that the quantum would carry momentum, as well as energy, making the case of a particle much cleaner. So in relativity, the energy of the energy momentum and the rest mass of the particle are related by this mass momentum energy momentum relationship, that is E square minus P square C square is equals to m square C to the power 4. And from this I would say and compute the classical equation of E is equals to P square by 2 m. And of course one can express the energy and momentum of the particle in terms of the velocity like this: E is equals to mc square over root under 1 minus b square by c square, and P nothing but mv times 1 upon v square by c square. So if a particle that moves with the speed of light like the photon must have the zero rest mass, and otherwise its energy and momentum would be infinite due to the vanishing denominators. So with the rest mass set to 0, this equation, this equivalence relation, rest mass set to 0, and this equation becomes E nu is equals to P nu times C, and this H nu is equals to C. We can write P nu is equals to E nu upon C, that is H nu by C, that is H by lambda, right? And we see this relation again later when we discuss the matter waves, right? So from this if the unpolarized light incident on an electron, that is, if this is the wave, right, which is unpolarized, is incident upon the electron, right, this is electron, scatters into an angle theta. If this scatters into an angle theta, then classically this is described by Thomson scattering. The light does not change frequency during this process, right? So but however the X-rays of a carbon target or X-rays correspond to the photon energy in the range from 100 electron volt to 100 kilo electron volt. The classical counterpart of the Compton experiment is the scattering of electromagnetic waves of free electrons called Thomson scattering. Here an electromagnetic wave is incident on an electron, and the electric field of the wave shakes the electron, which oscillates with the frequency of the incoming field, and the electron oscillation produces a radiated field of the same frequency as that of the incoming radiation. So in classical Thomson scattering, the differential scattering cross section is d sigma upon d omega is nothing but E square upon mc square whole square half 1 plus cos square theta, right? And where theta is the angle between the incident and the scatter wave, and the radiated energy at the same frequency as the incoming light. And this is depicted in this figure, where the unpolarized light is incident on the electron and theta is the angle of scattering. So if the cross section has units of length squared or area, as it should, it represents the area that would extract from the incoming plane wave and the amount of energy that is scattered by the electron. Indeed, the quantity, this quantity E square upon mc square is called the classical electron radius, and it is about 2.8, femtometer, right, which is much bigger than a proton. which is much bigger than a proton. And if we treat the light as photons, and the elementary process going on is a collision between two particles, an incoming photon and roughly the stationary electron, two facts can be quickly demonstrated. The photon cannot be absorbed by the electron, and it is inconsistent with the energy and the momentum of the observation. Let's try for the Compton scattering slide. When this is the scattering, where you can see the process of collisions of the electrons, and particularly the radiation of high energies, particularly X-ray or gamma rays energies. So this is the schematic diagram where incident photons are being incident on electron, where this is the path of the scattered photons, this is the typical angle, this is the oscillating electron, and as we mentioned that this is the Thomson scattering. Particularly this type of behaviors are being studied, and this is a much more complicated equation, I would say, but the general intention of doing this is the photon must lose some energy, and thus as we see from this picture, you can see very carefully you mention in this diagram that if the photon must lose some energy, and thus the final photon wavelength lambda f must be larger than the initial photon wavelength lambda I. This is clear in the laboratory frame, where the initially stationary electron must recoil and thus acquire some kinetic energy. And if we plot this in the diagram over lambda versus, this is my lambda and this is my intensity, right? Then the initial wavelength is like this, and this on the this larger peak is the lambda f, right? So if this is our lambda I, and this should be our lambda f. Obviously lambda f is higher than the lambda I, and this particular diagram is the Compton scattering experiment, and the incident photon wavelength is lambda I, and the scattered photon wavelength lambda f is particularly this has the relation that lambda f is nothing but lambda I plus LC, and our LC is from our previous doing that the Compton wavelength is denoted by LC, right? This is our Compton wavelength, that is LC, that is the dimension of length. So this is a particular behavior where our scattered photon frequency wavelength is nothing but the initial plus lambda c, and the corresponding theta is obviously 90 degree. So as of now, as we discuss, and let's wrap up our discussion today, which is the particle nature of light and the wave nature of matter. The last important discussion of today's lecture is the Compton observed did not agree with the predictions from the Thomson scattering, as we discuss. So the X-rays changed frequency after scattering, and a calculation using energy and momentum conservation shows that the change of wavelength is correlated with the angle between the scattered photon and the original photons, and this particular behavior lambda f is nothing but lambda I plus h upon mec over 1 minus cos theta, and this is also lambda I plus LC times 1 minus cos theta. So as we note that the appearance of the Compton wavelength of the electron, the particle the photon scatters off from, and the maximum energy loss for the photon occurs for theta equals to pi. That is maximum, that is cos theta equals to -1, that is 2 times LC. So this is a very important message, where lambda f turns out to be theta is equals to 180 degree, that is lambda I plus twice lambda c, that is the Compton wavelength. And the maximum possible change in wavelength is 2 lambda c, and theta, for theta is equals to pi by 2, that is 90 degree, the change of wavelength is exactly LC, that is lambda f for theta equals to 90 degree is lambda I plus exactly lambda c. The Compton experiment used the molybdenum X-rays with energy and wavelength, particularly E nu is equals to 17.5 kilo electron volt, and lambda I turns out to be 0.07 nanometer. And the incident of the carbon target, placing the detector at angle theta equals to 90 degree, the plot of the intensity or the number of photons scattered as a function of wavelength is already shown in this figure, where the second peak at the original wavelength lambda I is equals to 0.0709 nanometer, and the peak at lambda f is the expected lambda f minus lambda I, that is 2.2 picometer, which is about the Compton wavelength of 2.4 picometer, given that the photons have their energies of 17 kilo electron volt, and the bound state energies of carbon is about 300 electron volt. So since the mass of the carbon atom is several thousands of times larger than the mass of the electrons, the Compton wavelength of the atom is much smaller than the electron Compton wavelength, and there should be no detectable change in the wavelength of the photon. So this is our discussion for today. Thank you. See you in the next lecture.